Recently, I was looking for a video that explains impulse responses without using any equations, so I could send it to musicians who are math averse. And I couldn't find one that actually imparts a good understanding of what impulse responses are and what they do. So I'm making that video. An impulse is the shortest possible sound. In digital audio, that means it's one sample long. The one sample can be any value, and any other samples are zero. In analog sound, an impulse has literally zero length and infinite amplitude, so it's purely theoretical. It's impossible in the real world. Frequency-wise, an impulse contains an equal amount of every frequency. In digital sound, that of course means everything from 0 up to half the sample rate. In analog sound, it means every frequency up to infinity. Like I said, impossible. Of course, if you convert a digital impulse to analog, you won't get an analog impulse, you'll get a band-limited impulse, which looks like this. An impulse response is what you get out of some system when you put an impulse in, where a system could mean an equalizer, a speaker cabinet, an instrument body, anything that modifies sound. In a lot of cases, the impulse response is all you need to know to emulate that system. In those systems, if you put in impulses of different amplitudes, you get out exactly the same impulse response each time, only scaled by the amplitude of the impulse. You put in half as much impulse, you get out half as much impulse response. That means it's linear. Distortion effects are nonlinear, so you can't emulate them with an impulse response. You might notice that I haven't played an impulse so you can hear what it sounds like, and that's because it's a horrible sound. It's like a really bad electric crackle from a loose cable. It could even damage your speakers. But here's an impulse response of a simulated concert hall. And here's what that sounds like applied to my voice. It's a pretty good reverb effect. The trick to understanding how impulse responses work is to notice that every sound is equivalent to a series of impulses. In analog sound, you need an infinite number of impulses packed infinitely close together, and I don't recommend thinking too hard about that. In digital sound, it's simple. This sound, containing 20 samples, is just 20 impulses at different times, with nothing between them. When you put an impulse into a linear system, you get out its impulse response. When you put in 20 impulses, you get 20 impulse responses. Each one starts at the same time as its corresponding input impulse and is scaled by its amplitude. If the impulse is negative, that means the impulse response is phase inverted. They overlap, so they're just added up as if each one was in a separate track of your recording software. This process of scaling and adding up all the copies is called convolution, which is why the desktop plugins are called convolution reverbs. It'd be easier to call them convolvers, and more accurate because they can be used for things other than reverb. The pedal effects, called IR processors or IR loaders, are also convolvers. They're the same thing, except they have a much lower limit on the length of the IR. Besides reverb and echo effects, you can also do any kind of frequency filter or equalization with impulse responses. To see how this works, let's start with a response consisting of two equal pulses, 20 milliseconds apart. It's equivalent to a delay of 20 milliseconds with an equal mix between the original sound and the delayed sound. Most of you will probably know this will have a weird phasey effect like this, because some frequencies are cancelled out and some are reinforced. It turns out that if you do frequency analysis on an impulse response, the spectrum that gives you is the frequency response when you apply that IR to another sound. So for any frequency response you want, you can do the inverse of frequency analysis and synthesize an IR. The only catch is, most of the time it gives you an IR that's infinitely long in both directions. Luckily, a lot of the time it's got really thin tails, which you can just chop off without making much difference, giving you a nice short impulse response that you can use. But most of the time, we don't even bother with trying to specify a frequency response. We just run an impulse through the thing we want to emulate, record the output, and use that. Or better yet, instead of an impulse, we use another wide spectrum sound like a sine wave sweep. That way we don't have to try to generate a real impulse sound and hope that it doesn't damage anything. And then we can deconvolve the recording with the sound we used, which gives us what we would have gotten from a perfect impulse. Deconvolution is some tricky math, but there's software that can do it for you. Convolution has a few properties that might be useful to know. One is that it's commutative, which means if you're running your sound through two impulse responses in a row, it doesn't matter which order they're in. Of course, if there's something else in between them, it might make a difference. It also means that you could swap the input signal with the impulse response and get the same output, assuming the input signal isn't too long for your effects processor. Convolution is also associative, meaning that if you have two in a row, you can combine them into one. Just convolve the two impulse responses together and use that by itself. Talking about commutative and associative properties is starting to sound a bit mathy. So I'm going to stop there before I get carried away and start trying to teach you about the beautiful duality between time domain and frequency domain. I hope this was useful. If anything wasn't clear, feel free to ask questions in the comments.